Mine is on. Can I just go? So hi everyone, my name is Bart. I'm a software engineer working for Scylla. I'll be talking about what we're doing to introduce stronger consistency guarantees into the database by implementing Raft. So before we go into Raft, how many of you are familiar with Scylla? All right, so not that many, so I'll start by going over a brief introduction. Scylla is a NoSQL database compatible with Apache Cassandra. We implement the same APIs, and we use the same file formats. We are, however, much faster. We have 10 times the throughput at much lower latencies, especially the higher percentiles. The database is also self-tuning. We employ a lot of control theory to make sure we can schedule all the different user workloads and that we can balance them with the internal processes that the database has. We use ODirect and bypass the page cache, so we do fsync correctly. And the database is written in C++ with a lot of attention paid to the underlying hardware, which we want to fully utilize. So we are a dynamo system, so there's no special nodes. A particular piece of data is replicated across a set of replicas, and the full data set is partitioned across the whole cluster. When a user performs a read or write, he can specify the consistency level, which is how many replicas should acknowledge the operation before it is considered successful to the client. The data model is based on tables. The tables can have many columns. There's a primary key with two components. The partition key are a set of columns that specify how the data is distributed across the cluster. So they determine which nodes get to handle which pieces of data. And then there's the clustering key, which defines the order in which data is sorted and stored on disk. In terms of consistency, when we are performing a write, the coordinator node that handles the user request is going to replicate that write to all of the replicas. We can, as I said, specify the consistency level. So if we say we want a quorum, a majority of replicas to acknowledge the write for it to be considered successful, then we can tolerate one failure, one replica not receiving the write. If we then do a quorum read, and let's say that we only read from one of the replicas that had the data that we wrote previously, then we are going to consider the operation successful, and we are going to return that piece of data. This provides us with some consistency guarantees, namely read-your-own writes and monotonic reads. And during this read, we are going to notice that a replica was missing that particular piece of data, and we are going to propagate it there. We also do this in the absence of reads by having a background anti-entropy process called repair, which periodically ensures that all the replicas converge on the same values. There's a peculiarity, which is when, let's say, we're doing a quorum write and two replicas fail. So only one replica acknowledges the write. In this case, the user receives an error, but one of the replicas did store the new value. So repair will, in time, propagate that value over to all the other replicas in the system. So the user write failed, but the value made it into the system, and it's going to be observable by future reads. Another part of the consistency model is how we deal with concurrent updates. So if you're trying to update the same key and the same column to different values, how do we specify which one wins? And more importantly, how do we make them be commutative so that all replicas eventually choose the same values? And the technique we employ is the same as Cassandra's, so last write wins. We look at the timestamp and we pick the value that has the highest timestamp. If the timestamps match, then we pick whichever is the highest value according to the underlying data type. This is really not a great solution because timestamps don't capture intent, and we are also silently discarding one of the values that the user was trying to write. And the solution to this right now would be to make changes to the data model. So model the data as an appending log, make all writes be idempotent, workarounds like that. So another particularity of Scylla is that it is implemented on top of the C# framework, which is a C++ framework we wrote ourselves, but it's used by a bunch of other projects. And it's used for high-performance applications. So it imposes a thread per core design, in which there's one thread pinned to a particular CPU, and only one. And that means that if you want to fully utilize your CPU, then there can be no blocking ever. Otherwise, the CPU will just go idle. Because of that, C* provides a set of asynchronous APIs, not only for networking, but also for file I/O and multi-core communication. So in C*, data is confined to a particular core, and when another core wants access to another one's data, it uses message passing to fetch that data. And we expose these APIs as, in the future promise API. So for Scylla, this has the consequence that all of the components of the request path are replicated per CPU. And also, data is, like it is partitioned across the cluster, it is also partitioned inside a node. We use the same partition key to decide which CPUs get to handle which subset of the data. We use the middle bits of the partition key just to avoid aliasing situations when the shard count per node approximates the node count in the cluster. So the reason we want to introduce a stronger consistency model in Scylla is trivially because it just enables more use cases. If you want to have uniqueness constraints, if you want to specify that a particular email address exists only once in the database, then it's really cumbersome to do that with just quorum reads and quorum writes. If you want to have read, modify, write accesses where you read a value, make some decision, and modify the value and write it back, you can't really do that safely in the presence of concurrent updates with the mechanisms we have right now. Similarly, if you want an update to be all or nothing, so if you want all the value to be written on all the replicas or at none of them instead of those partial writes that we saw, then we have no mechanism to prevent that right now as well. Of course, we want these stronger consistency operations to be opt-in. We don't want you to have to pay for what you don't use. So Cassandra exposes this feature as lightweight transactions, which provides strong consistency per partition, so per key. It is essentially a distributed compare and swap. So you specify the new value, and you specify what has to be there for the new write to apply. It's not really a full transactional API, and so you end up having to write your programs like you'd write lock-free algorithms. So you make some modifications to some table, and then at the end, you try to update a pointer to the new data, and by having clients coordinate on this pointer, then you get the strong consistency properties. It is a data path operation, so we want to make it as high performant and as available as possible. And finally, because of the way the feature works, it does require an internal read before write, so we fetch the current value and are able to match it against the preconditions that the user is specifying. So to implement strong consistency, typically resort to consensus algorithms. Consensus is the process by which a set of replicas reach agreement over a particular value. They provide, consensus protocols provide consistency guarantees about the underlying data, and they are leveraged to implement what's called replicated state machines, where a set of replicas apply the same operations and in the same order and work together as a single coherent unit. We can tolerate some non-Byzantine failures, so for 2 times f plus 1 nodes, we tolerate f failures. And a run of the consensus algorithm is typically called a round, and it advances the underlying state. There are a set of guarantees that make these protocols worthwhile. So that of stability, if a replica ever decides a value, then that value stays decided forever. Agreement, that no two replicas should decide a value to different values. validity, that if we decide on a value, then it's because a replica did propose that value, didn't come up out of thin air. And also very importantly, that of termination, that eventually all replicas do reach a decision. So how do we go about choosing an algorithm? And there are two very popular ones, Paxos and Raft nowadays, but there are other ones. So first of all, we want to look at an algorithm that's understandable. So there was a very famous paper that came out of Google detailing their experiences implementing Paxos for Chubby. And basically the gist of it was that Paxos was a very underspecified algorithm, and that they had to search all of the literature to come up with Frankenstein of a solution. So we also want the algorithm not to be too cutting edge. We want there to be some real world usage of it and some experience and validity. Another thing to look at is how many, what's the overhead of having all those replicas coordinate to decide on a value. And that's usually in terms of round trips for agreement to be reached. Another thing is general performance. How amenable is an algorithm to typical optimization techniques? And an important trade-off is whether there's a strong leader or whether any replica can decide a value. So if the latter, then we require at least 2 round trips to decide on a value. This is classical Paxos or the new algorithm Cas Paxos. Cassandra does something similar, but they require 4 round trips. The other approach is to have a strong leader. So we go through a process called leader election, select one of the replicas to be in charge, and then we can commit values with 1 round-trip communication between the leader and the followers. This is what multi-Paxos, Raft, and Zab all do. Aside from this, there are a bunch of challenges in implementing these algorithms. So they typically rely on a write-ahead log to order operations, which takes space, and we need to find ways to compact that log. Also, read-only requests typically require a full run of the consensus algorithm, but we just want to read the latest value. We shouldn't have to go through that. So there are a bunch of optimizations that apply to some algorithms. Dynamic membership, having nodes come and go from the cluster, is also a big issue. The other one is multi-key transaction support. Can we extend the algorithm, or can we compose the algorithm to make sure we can have multi-key transactions? Another thing to look at is performance over the one. And finally, whether there is actually some formal proof of its safety, or whether there's like a Jepson blog post about it. So, not surprising, given the title of the talk, which was Raft. It is focused on understandability. It's a very descriptive algorithm. It is very widely used. There are a lot of implementations, and it's running in a lot of databases. It has strong leadership. There's a leader election process. And in the context of lightweight transactions, it is going to be the leader that does that read before write and validates whether a transaction can apply or not. And for us, the fact that there is a log of operations is no big deal because we can easily compact it, as we shall see. So in Raft, a node can be in one of 3 states. It can be a follower, a candidate to become a leader, or the leader itself. If it is the leader, then it is the one that handles user requests and carries out the read before write in the context of LWT and applies a new value and replicates it to the followers. It is also in charge of sending periodic heartbeats to the followers to keep them devout. And if the leader becomes unavailable, one of the followers will notice, will become a candidate, and will propose itself for leadership. A candidate will become a leader if it receives votes from a majority of the other replicas. In Raft, we have 3 components. We have the main consensus module that drives all of the algorithm's logic. We have the log, which implements this write-ahead log, which is the thing that actually provides most of the guarantees of the protocol. And when those entries of the log are safely committed in a majority of the followers, then they are applied to the state machine, which in the case of Scylla, the state machine is the database itself. And of course, then the client observes the data in the state machine. The algorithm provides a set of guarantees that makes it very understandable. So the election safety guarantee means that at any given time, there is only one leader in the system. The leader is the only replica that can append entries to the log. The Raft enforces through the log matching property that if two logs, that of the leader and one of the followers, contain the same entry at a particular index for a particular term, then the logs are identical up until that point. If that is not the case, then the leader will send whatever entries the follower may be missing, or will remove from the follower whatever extraneous entries it might have. In Raft, for a node to be elected leader, it needs to be at least as up to date as the previous leader. And finally, if a log entry is applied to the state machine in a particular replica, then it is guaranteed that the same entry is applied for the same position of the log across all the other replicas. This is how we guarantee that all the replicas are in fact working as a replicated state machine. So in Raft, time is divided in terms. Each term is comprised of the leader election process, and from this, it can result that we're able to elect a leader, or maybe no node received the majority of votes, so the process needs to be repeated. But time in Raft is logically divided in these terms. So applying this to Scylla leads us to a bunch of interesting design choices. So first of all, because Scylla is partitioned, there is no single node that holds all of the data. So even if we wanted to have a single leader for the whole cluster, it would be very cumbersome because it would need to contact other nodes that actually hold the data to do the read before write, and then to eventually apply the read, the write, all the while holding some logs that would prevent other concurrent operations from continuing. And it would also mean, obviously, that if all the write operations had to go through a single node, it would prove to be a huge bottleneck. So what we do instead is we have as many Raft groups as there are partitions of the token space. So for each token range, there's a set of replicas that handle that subset of the data, and those replicas form a Raft group. So there are many leaders and many Raft groups. A nice consequence of this is that we can have higher concurrency. So all writes can go to different leaders, to different Raft groups. And if one of those leaders fails and we have to elect a new leader, there's going to be a brief period of unavailability. However, this will only affect a subset of operations. There's some fine print next to this because if we have n nodes, then if one leader, let's say we have 10 nodes, if a leader dies, then we're going to lose 10% of our token ranges. So if a client is making random requests, then there is a 1/n probability that it will hit a key for which the leader is unavailable. So it doesn't mean that we beat the cap theorem, we're still going to be unavailable under the presence of failures. Because of how Scylla is implemented on top of C***, each group itself is going to be sharded on a particular node. So a shard or a CPU is going to handle a subset of the operations of that particular Raft group. This is going to impact how we organize those Raft logs. So inside a particular node, we are going to have many of these Raft groups. Have here the typical Raft modules, the core consensus module, and the log, the database. The state is going to be whatever persistent state we are going to need to keep across reboots. And then the RPC module is just what we use for messaging between replicas. So each shard, each CPU is going to have an instance of all of these groups. However, shared between all of these are going to be the heartbeats module. So if a node is a leader for many groups, and there's a follower that's a follower for many of those groups, then we don't want to send n heartbeats. We want to coalesce the heartbeats into just one message and send just that one heartbeat. This is how the simplified write path looks like inside a node. So we have a mutation, which is how we represent write requests in Scylla. The mutation is idempotent and commutative, and a set of restrictions against which we are going to compare whatever is on disk. So first, we apply some locks to ensure that concurrent operations are blocked. We query the database to find out what's the current value. We compare that against a set of restrictions. And if they match, then we apply the entry to the log. From there, we communicate with the followers to try and replicate that log entry. And when we finally replicate it to a majority of followers, that entry is committed. And committed entries can be safely applied to the database. So sharding then is where all the differences between a typical Raft implementation and this one are going to arise from. So first of all, you notice how we organize our Raft groups per node. But inside a node, each shard handles a non-overlapping subset of the ranges. So why didn't we organize the groups by shard instead? And the reason is that this would lead to combinatorial explosion of state. So the metadata for all of those groups would overwhelm the database. In Raft, a particular entry is identified by the term that it was written in and by the index in the log file. So in Scylla Raft, we add to that what was the leader shard that entry belonged to. We're going to have to be careful with heterogeneous clusters. These are clusters where the shard count is different between nodes. And this is not a typical situation, but it can happen during a rolling restart where someone is provisioning more CPUs on their machines. And for a short while, shard count is going to be different among the nodes. And also resharding, which is when one of those nodes reboots and comes up with a different shard count. So if we were dealing with a homogeneous cluster, then everything is fine. Shard 0 of node 0 is going to talk with shard 0 of some other node. And their logs are going to be exactly the same and organized the same way. If, however, we have different shard counts, it can be that different leader shards are talking to the same follower shard. This means that in the follower's log, these entries are not going to match how they're ordered in the leader logs. In particular, for the log matching property of Raft, when we send the new log entry, we also send what we expect there to be before. So the follower can check if its log is up to date to the expectations of the leader. And if it's not, then we trigger that process by which the follower is brought up to speed. In this case, the follower can have entries that another leader shard gave it, and they won't match what this other leader shard is expecting. We could solve this by going over and filtering out entries in the log, but it will be cumbersome. We can have a similar scenario where the leader shard is talking to different follower shards. And in this case, the logs in the follower shards are going to have gaps in them because some of the entries went to another shard on that machine. And here is the same thing. When we're trying to append an entry, the log matching property will require that we look at what's in the log, and we're going to find gaps there. And the algorithm is going to assume that it's missing data. So it won't work very well. So to solve this, we change how logs are organized. We organize them by term, because for a particular term, the leader shard count is stable. And then we also organize them by leader shard. When a leader restarts, then its term ends. It has to go through another leader election. In other words, whether a node is a leader or not is not preserved across reboots. This is why if you're changing the CPU count of a node, you have to go through a restart. So this means we don't have to worry about a leader resharding in the middle of its term. And because now in the followers, logs are organized by leader shard, It can be that in some cases, different shards have to access the same log. So they will require synchronization. This goes a little bit against the philosophy of C*, where everything is partitioned. But this situation is really not typical. So we do require some synchronization here. So finally, log compaction. As I said, when entries are committed, replicated to a majority of followers, they can be written into the database. At this point, we can compact the log and get rid of all of these committed entries. In other words, it means that the database itself is now going to be responsible for that prefix of the log. This has consequences when we are dealing with a follower that has fallen behind and needs to be brought up to date. So whereas before we could just ship the log entries over to that node, now we have to look into the database state and figure out what that node is missing. Fortunately, we already solved that problem. We had exactly the same problem with diverging replicas. So we can use that anti-entropy process that we call repair to figure out exactly what piece of data follower is missing and then transmit only those mutations over to it. There are some interesting aspects to this. Due to natural concurrency, it can be that what we're transferring to the node actually overlaps with entries that are in the log that we are also shipping over. But because our mutations are idempotent and commutative, no harm comes of this. And it's also the case that repair is a heavyweight process to run, so we'd like to avoid it. So if we notice that we have some followers that are falling behind, we can choose to keep some committed log segments around, let's say 1 gigabyte worth of log segments around, just to make it much faster to bring those followers up to date. It's much faster to just send sequential pieces of data over. Now, the most difficult aspect of all of this is membership changes. So as we saw, and there will be many Raft groups in the Scylla cluster. It's going to be for each key space, we are going to have replication factor times the number of vnodes, which is how many token ranges the key space is divided in Raft groups. So many Raft groups. And Raft has a restriction on the configuration changes. It specifies that only one node can be added or removed from a group at a particular time. So if we want to have more complex changes, these are going to have to be implemented as a series of these single-step changes. In Scylla, unless you are changing the replication factor of a key space, the member count of a group is going to remain the same whenever you're adding or removing a node. So this means that if you are adding a node to a group, you'll have to later remove one of the nodes from that group. And conversely, if you are removing a node. So we have here a segment of the key space in which node A is the primary replica for a particular token space. So it's going to form a Raft group, and replicas nodes B and C are going to be the secondary replicas for that token range. So these three nodes are going to be in a Raft group together. And the same thing for B. It's going to be the primary replica of that particular token range, and C is going to be in a group with it, and whatever node comes next. Now, if I want to bootstrap a node D, and D claims a token range that falls between A and B, some things are going to happen. Namely, now D is going to be a secondary replica for A, and C is no longer going to be in that Raft group. The ranges for which B was a primary replica for now have changed, because some of those ranges now belong to D. And because of that, now D is also a primary replica for a new token range. And B and C are going to be in a Raft group together with it. Out of all of these things, what's important is having node D join the group of A and having node C leave it. Raft forbids that these two operations happen concurrently, so we have to order them. And this is actually requires changes to how our group membership algorithms work, our existing ones. So before we bootstrap a node, we need to wait until the node has joined all of the groups. And this is when we know that it's safe for now the other nodes to exit those groups. Doing a single operation at a time, like Raft requires, has the nice property of ensuring that the majorities of the configuration before overlap with the majority of the configuration after the change. Also, these configurations, what replicas comprise the Raft group, are written as special entries to the Raft log. So this has the drawback that now bootstrapping a node or removing a node is going to be a much longer process because it requires consensus rounds across all of the groups, many of the groups in the cluster. So adding or removing nodes becomes much more expensive. And finally, new nodes, because they don't hold the data, they enter the system as non-voting members. So they can be sent log entries from the leader, but they can't really participate in the leader election process. This can also hurt availability in some cases. So this is it for Raft, and for everything I've said was applying to single key transactions as I showed to the user as in the form of LWT. However, LWT has another important constraint, which is it has a consistency level that says a transaction should only apply within a particular data center. This means that our Raft groups cannot contain replicas from multiple data centers. It means instead that each data center has its own Raft groups. So now we are left with the other problem because there's also a consistency level that says the transaction should apply across all data centers. So now we need to have some sort of way to coordinate among Raft groups. This is more work upfront to support LWT, but it's actually a subset of what is needed to support multi-key transactions. So the way we solve this is by layering an agreement protocol like two-phase commit on top of Raft groups. So other databases like CockroachDB do this. So it's a typical two-phase commit implementation with the benefit of all of the participants, like the resource managers or the coordinator or the nodes that are going to hold a transaction status being fully replicated and fault tolerant because they form Raft groups. I'm not going to go into details. It's typical two-phase commit with additional fault tolerance. So I've spoken about how external users can benefit from strong consistency, but the database itself can also benefit from it. One example are concurrent schema changes. So today, schema change is carried out locally in whatever replica the client contacted, and then propagated throughout the cluster. This means that we don't have any protection against concurrent schema changes or changes that are done in incompatible orders. So for example, if I'm trying to create a table on one side, and on the other side I'm trying to drop a user type that's used in that table, and there's really no way to order these two operations. And because they are concurrent, there's really no way to provide a good error message to the user. So this is just going to be errors in the logs later. However, if we say that if we partition our key spaces, like the key space name, if we partition that into the cluster, then we're going to reach a Raft group that can be responsible for all operations for that key space. And once we have that, then we can use LWT when we are applying schema changes, so that they all go through the same leader, and then they are ordered, and we can provide nice error messages to the users. Another thing are range movements. So currently, we can't really have concurrent range movements. We can add more than one node at a time because they can pick conflicting token ranges. And whenever a node joins the cluster and picks whatever token ranges it wants, it will do so randomly. So it's not really optimal. So what we want to have is a strongly consistent way of ensuring that when we're adding a new node, that we actually give it whatever token ranges will be best for the system. Like we can see which nodes are more overloaded and take ranges away from them and give them to the new node. It also means that we can tell the system that we want to add many nodes at the same time, and the system can pick tokens in a way that will make those operations actually be able to proceed concurrently. Of course, they wouldn't be able to be in the same Raft groups, but we could do better than what we have now. And the only thing is that we can't use the same partitioning approach that we could use for schema updates, because picking a token is a centralized decision. It applies to the whole cluster. So we could do one of two things. We can have a global group. We can say all nodes in the system belong to a single Raft group, which is simple but has many disadvantages. Or we could say that the Raft group that coordinates cluster range movements is formed by very specific nodes. So we can say that the seed nodes, the ones that everyone knows about, are the ones that form this Raft group that controls range movements and token ownership. Finally, materialized views. This materialized view is a derived table from some base table. It is typically used to index a column out of the base table, but it is different than a secondary index because you can actually denormalize data in it. So you can include in a materialized view many columns from the base table. A materialized view is handled by a totally different set of nodes than the base table. And it cannot be written to directly. So when a base table is updated, the database will process those updates as well, will calculate the view updates that are needed to update the materialized views, and are going to send it to the view replicas. It does so in the background and in an eventually consistent fashion. This has the advantage of preserving base table availability. So if one of the view replicas is down, or all of the view replicas are down, the base write is still going to succeed. We're just going to accumulate in memory the pending view updates. This can be a problem because of two reasons. One, we can have issues with consistency, with keeping the views up to date with the base tables. And it also means we can have issues with flow control. All of those pending view updates in a base node can start to take over all of the memory, and then we need a distributed flow control solution, so we are able to communicate that resource pressure over to the coordinator node, which in turn is able to slow down the client. So it becomes very complex. With multi-key transaction, we could instead specify that the base table be updated together with the view table in the context of a single transaction. This will ensure that they are kept always consistent with each other and would provide natural back pressure from the view replicas and base replicas to the client. And this would, of course, have to be opt-in, and because it will come at a performance cost. And that's it. That's all I have on the subject. So if you have any questions, I'll take them now. Thank you. Oh. So just repeat the question. Okay, we will.
What's the general idea behind supporting multi-tenant workloads while still having a single core working on a particular workload?
So the question is how we support multiple workloads.
Basically avoiding head-of-line blocking for a single.
Okay, so how do we avoid head-of-line blocking by having a slow shard? So the question to that, or the problem is similar to how it is handled by having different nodes. If you have a slow node, you're going to have the same problem. And the way that is solved is by better data partitioning. So if the way you select your partition key is picking hot nodes, then you're going to have to employ a different partition key. The same thing happens with shards. So a good partition key is going to ensure that all shards are balanced and doing roughly the same amount of work. If you have a hot shard, then there's not much we can do about it. It's like having a hot node, and it's up to the user to tweak the partitioning key. Make sense?
So if a number of lightweight transactions come in for keys in a single range, it prevents progress on things that come in behind it until those transactions complete?
No. So I didn't mention that, but when I was showing the request path and we were taking locks, so there's an opportunity to allow a lot of concurrency there. So if we're talking about different keys, then they will take different locks and they will be able to progress independently within the node. Any other questions? I don't think so. Okay, thank you.